Swayam Prabha. Digital India. Educated India.
We will now consider an RC circuit example with a step input which is not 0. Okay. Let me make the circuit slightly more complicated by having two resistors and a capacitor here. Okay. This is still nonetheless very easy. So let's say this is 2 kilo ohm and this is 3 kilo ohm resistor, and this steps from 0 to 10 volts at t equals 0, and we have a capacitance which is, let's say, 10 nanofarads. Okay. Now, though we have two resistors, this can be effectively reduced to a single voltage source in series with a single resistor at the terminals of the capacitor using the familiar Thevenin equivalent. Okay. So, if these are 1 1 prime and whatever I have on this side, I change to Thevenin equivalent. I won't show the steps, but you can work this out for yourselves. I'll have some Vs in series with a resistance. The resistance happens to be the parallel combination of these two. Okay, and that will be 2 kilo ohms times 3 kilo ohms divided by 5 kilo ohms, which is basically 1.2 kilo ohms. And this Vs you can again compute by the usual procedures used for Thevenin equivalent calculations. It will jump from 0 volts to 6 volts at t equals 0. So please do the Thevenin equivalent calculation yourselves. And we have a capacitor which is 10 nanofarads. Okay. So this is now the familiar circuit. Now whatever initial condition is there on the capacitor will still remain. So let me say that the initial condition is 1 volt. Okay, it happens to be there at t equal to 0 just before the step is applied. This has 1 volt. And in this circuit, the capacitor is in series with the resistor, and we can't have infinite current through the capacitor which will induce a step change. So the voltage across the capacitor will be continuous, and even after the step is applied, we will have 1 volt. Okay. So we have calculated all of these things in general terms. So this means that Vc just after the step, Vc of 0 plus is also 1 volt. Now we know the general form of the solution. You can do this in many ways. So Vc of 0 plus is 1 volt. This is because of continuity and no infinite currents. Okay. Then Vc of infinity, which is the final value, is computed by assuming that the capacitor is an open circuit. This is an open circuit, then the resistance here, it doesn't have any voltage drop across it. So all of Vs appears between the terminals 1 and 1 prime. Okay. And Vs, the final value is 6 volts. The 6 volts will appear there. Okay. And the time constant tau, of course, is, if you set Vs to 0, we will have this RTH across the capacitor. So it is 10 nanofarad times 1.2 kilo ohms. It is 12 microseconds. Okay. So we can easily write out the expression, right? We know that Vc of t is Vc of infinity plus Vc of 0 minus Vc of infinity exponential minus t by tau, which is 6 volts plus the initial value 1 volt minus 6 volts exponential minus t by 12 microseconds, which is 6 volts minus 5 volts exponential minus t by 12 microseconds. Okay, so that's the expression for it. And you can do this in many ways. Basically, the point is to be able to identify the time constant and the initial and final values. Okay, now even if you didn't reduce it to the Thevenin equivalent, you had this circuit and wrote the differential equation for this circuit, you would get exactly the same answer and exactly the same differential equation, of course, in terms of the capacitor voltage Vc. Okay, and instead of Thevenin equivalent, you could have converted it to a Norton equivalent. Okay, so again, I am not going to show how to convert it to Norton equivalent, that you already know from earlier lessons. So the Norton equivalent, let me put down the original circuit. This steps from 0 to 10 volt. Okay, so now if there is a step change in the voltage source in an independent source in the circuit, then the Thevenin voltage or the Norton current can also show the same step change. Okay, so we had, this is, let's say, Vi, and it changed from 0 to 10 volts, and we have 2 kilo ohms and 3 kilo ohms, and across these terminals we have the capacitor C, which is 10 nanofarad. Then the Norton equivalent of this part of the circuit will be the current, which is the short circuit current, and it will jump from 0 to 5 milliamps at t equals 0. Across it we will have a Norton resistance, which is the same as the Thevenin resistance and equals 1.2 kilo ohms, and we have a 10 nanofarad capacitor across it. Okay, so now again it's quite easy to solve. This gives you a slightly different viewpoint. Now what happens is that again, let's assume that Vc of 0 minus is 1 volt, and we don't have infinite currents flowing through the capacitor, so Vc of 0 plus will also be 1 volt. Okay, so I'll show this as a sketch. So at t equal to 0 minus and 0 plus, we will have 1 volt. Okay, now what happens is, because we have 1 volt over here and 1.2 kilo ohms, so a certain current is taken away by the resistor. Okay, and that will be equal to 1 volt by 1.2 kilo ohms. The remaining current, 5 milliamps minus 1 volt by 1.2 kilo ohms. Okay, so that will flow through the capacitor just after t equals 0, and that will make the capacitor voltage become larger and larger. As the capacitor voltage increases, more current flows into the resistor. Eventually very little current flows into the capacitor, all of it flows into the resistor, most of it. So the rate of change of capacitor voltage becomes slower and slower and slower, and at t equals infinity, all of this current, 5 milliamps, will be flowing through the resistor, producing 6 volts across it, and no current will be flowing through the capacitor, which means that its voltage will be stable at 6 volts. Okay, so it starts from 1 volt and reaches 6 volts. Okay, and the equation will be exactly the same as before. Of course, it will be six volts minus 5 volts exponential minus t by tau. If you set the independent source to 0, we just have 1.2 kilo ohms across 10 nanofarad, which is 12 microseconds, and in fact we have to get exactly the same answer as before, otherwise we would be in trouble. Okay, so that's the expression for it. And this slope again you can calculate from the initial current flowing through the capacitor, because the slope of capacitor voltage is related to its current, or you can find it out by differentiating this expression. Okay.